Hello, this is again Mr. DeMuro, and this is our third video on nuclear chemistry. So far we have gone through discussing nuclear symbols, mass to charge ratio, and the types of natural decay. We also mentioned that many of the particles mentioned in natural decay, alpha, beta, positron, and so on, can be found on table O. Their notations, their symbols, their masses. All of the particles involved can be found on table O of your reference table, which is page 7. The next topic in our continuing series of nuclear chemistry videos is the nuclear equation. Now, in a nuclear equation, conservation of mass is, of course, paramount. Always make sure that the numbers on one side of the arrow match the other side of the arrow. Now, in all of these equations, we will always deal with a plus sign. Something plus something. Okay, whether it's a natural decay, kind of like decomposition reactions. You start with one reactant, you will have many products separated by that plus sign. As long as all of your products, when added together, total up to the original starting material, the equation is balanced. Artificial transmutation, artificial decay, which again will be discussed in a future video, will have plus signs on both sides of the reaction. Since we do something, we initiate a nuclear reaction. Therefore, our reactant side, the left side of the equation, will have more than one particle. Now, in this video, we are going to look at the nuclear equation, which is basically what does something break apart into. Okay, natural decay undergoes, as I said, basically a decomposition reaction. You have one reactant, one unstable isotope. When that radioactive isotope decays, it will turn into two products, and always two products. The particle that is released and the element that is left over. Now, in doing these kind of equations, the reference table is, of course, extremely important. There is a table on page 6. This is table N, selected radioisotopes. Now, again, quality of the video, things are a little fuzzy. But basically you have over here, which is called the nuclide. The nuclide is the symbol of the radioactive isotope listed in alphabetical order by symbol, with the mass number in question. This, of course, means that you, the student, must look up the charge. That's the nuclear charge, which is the number of protons in the nucleus, aka the atomic number. So very first on the list we have gold, 198. I know it's fuzzy, you just have to trust me. Okay, the second one has half-life, another part of nuclear chemistry that will be discussed in a future video. Over here, the third column, you have the most important thing for our topic right now, the decay mode. Okay, the decay mode is either listed as beta negative, which is your electron, beta positive, which is your positron or anti-electron, and a few of them here are alpha, which again, I understand a little hard to see in the video here, but if you have your reference table handy, you will be able to follow along and see what I see. Then finally you have the nuclide name, which is just the name of the element followed by the atomic mass, or in this case the mass number. For extremely heavy radioactive isotopes, it is the most common radioisotope. For everything else, it's the average atomic mass rounded off to the nearest whole number, which implies the most abundant isotope in question. However, on this list, only radioactive isotopes are listed, not the most abundant, not the actual rounded mass number. So our second one, you may recognize from Earth Science class, good old carbon-14. Okay, C14, carbon-14, is the radioactive isotope of carbon. Carbon has three isotopes. Carbon-12, which about 99% of the carbons in the universe are carbon-12. A slightly heavier carbon-13, which has 7 neutrons and 6 protons instead of the 6 and 6. And then carbon-14, which is actually not technically natural. It is actually generated from nuclear reactions. So carbon-14 has to be created by a nuclear reaction. It doesn't occur naturally on its own. It is created through some other process. Now, while that process is technically natural in creating carbon-14, again, carbon-14 cannot be found naturally unless something else makes it. As listed here, last year, your reference table in Earth Science listed the half-life of carbon-14 at about 5,730 years, or 5,700, or 5.7 times 10 to the third. Here we have the list, okay, 5,715 years. We also have here at the very bottom, and again, I apologize for the quality of the video, because it doesn't seem to want to focus, but we have the source, okay, it just tells you the source. We have a variety of units that this used to tell you the difference of. Okay, so the table actually used to define what the units were, but go through real quick. So if you can see, if not, if you're following along on yours, D stands for days, Y stands for years, MS stands for milliseconds, MIN, minutes, S for seconds. Okay. Anything longer than a certain number of years will be listed in scientific notation. So our usual ones, like uranium, okay, here we have uranium-238, and very accurately 4.47 times 10 to the 9th, which again, Earth Science was rounded to 4.5 times 10 to the 9th years, or 4.5 billion, with a B, billion years. When looking at the ratio of uranium and lead in any sample, we see that all the samples on Earth are about 50-50, meaning that in a 10-gram sample, 5 grams is uranium, 5 grams is lead. Using that very simple ratio, we have been establishing the Earth at about 4.5 billion years old. The ratio is not exactly 50-50. It's slightly higher on the lead side, implying that the Earth is a little bit older than the half-life of uranium. Estimates put the age of the Earth at about 4.6 billion years, whereas the half-life of uranium is a little less than 4.5. But again, that's for a future video. Right now, all we are concerned with is the nuclide, whatever its mass and mass number is, and atomic number is, and the type of decay mode. So, since we had mentioned uranium, let's use it. Okay, we have 3 to choose from. We have uranium-233, uranium-235, and uranium-238. Not that it matters, they all undergo alpha decay. Okay, so here's how this is going to work. We have our nuclide. So we'll start with uranium-238. Okay. It's a little fuzzy. So uranium-238 will naturally decay. Oops. Okay, it's going to naturally decay. So uranium-238, which we would look up on the periodic table. Again, table N gives us the mass number and the symbol, the name uranium-238. It is our responsibility to know where it is. Uranium is on the actinides, the very, very bottom row on your periodic table, which we can flip to page 9. And there it is. Okay, uranium is element number 92, third in the actinide series from the break. Okay, actinide number 89, thorium is 90, praseodymium is 91, and here is uranium, named after the planet Uranus, which is why 93 and 94, also named after the planets, is Neptunium and Plutonium. So Uranus, Neptune, and Pluto. Okay, so uranium-238, according to table N, which we have already established, undergoes alpha decay. So we can write that as one of the products. Okay, so we write the mass of the alpha particle and the charge of the alpha particle. As for the symbol, it is entirely up to you. Table O gives you the choice of using either the alpha symbol itself, over here, or copying the mass, number, and charge of helium using the symbol helium. Again, a little fuzzy, I apologize. Follow along on yours. Okay, so helium or alpha, either way. Okay, we can draw the symbol. So this is going to be released. So again, our arrow implies in decomposition we start from one reactant, we're going to form many products. Here, undergoing alpha decay, one of our products is alpha. That means that we are going to have another product, which we separate by the plus sign, as we do in all chemical equations. The thing is, this side, whatever two particles we have here, when added together, must equal what's over here. So to figure it out, we just do the opposite of this, we subtract. So 238 minus 4 would give us 234. Checking our work, 234 plus 4, 238. Next, 92. Uranium is going to lose 2 protons when an alpha particle is emitted. We start uranium with 92, that means we should only have 90 left. So 90, again, plus 2 equals 92. A quick check to the periodic table, and element number 90 is thorium, named after the Norse god Thor. So this is a good example of a nuclear equation undergoing alpha decay. Okay. Going back to table N, we can we'll choose an element. So let's see. Let's try calcium. Okay, calcium 37 undergoes, and you'll have to trust me if you're not having a table next to you, beta positive decay. Okay. Beta positive, according to table O, down here at the bottom we have beta negative, second from the top, alpha beta. Beta positive down here is a positron. Okay, so in our next example, if we have calcium 37, right? Calcium 37 undergoes positron decay. Positron is 0 over 1, and again, you can write this with the beta symbol or E. Now again, with these type of nuclear equations, we are missing the charge, the mass, the nuclear charge of calcium. Checking our periodic table, calcium is element number 20. Okay, now again, the nucleus of calcium is losing a positron particle. That means that there has to be something else left over when this particle is emitted. Now notice, the mass of a positron particle is 0. That means that you're not losing anything from your nucleus in terms of number of particles. The mass number remains the same. The number of particles is the same. It's the identity that changes. One of your protons and one of your neutrons has switched sides. It has become something new. Okay, in this case, a proton converts into a neutron. So the number of particles remains the same. So 37 minus 0 equals 37. All right, and again, checking our work. 37 plus 0 stays 37. Now, as for our bottom number, 20 minus 1 equals 19. And again, going backwards, 19 plus 1 gives us 20. Now, all we have to do is fill in the potassium is element number 19. Okay, so far we've had alpha decay and positron decay. And for the reagents, these two plus beta decay are the only ones you actually need to worry about. Okay, so our next one, beta decay. So, going from table N, let's select a good beta decay. We can try, well, let's go with carbon. Why not? Okay, so we have carbon 14. Carbon 14 is going to undergo beta decay. Okay, so again, natural transmutation. We have one element on the left breaking apart into many pieces. Our first of many pieces, the reference table tells us, is beta. -1. And as mentioned before in a previous video, this is where it's going to get tricky. This is where you have to be very, very careful with your math. And again, this is, with these natural decays, the trickiest one. So, going back, carbon has a mass of 14, but some of those are protons, which we need to write down here. Carbon is element number 6. Now, 14, if we lose a beta particle, we lose nothing with the mass. Okay, one of our neutrons is changing into a proton. So 14 on the top, 14 on the top. The top numbers equal each other. 14 plus 0 equals 14. Now, here's the tricky part. The 6, we are losing a beta particle. We are losing a -1. So 6 minus -1 gives us 7. Working our way backwards, 7 plus -1, or 7 minus 1 equals 6. Again, just making sure that the numbers on the bottom match and the numbers on the top match are functions. Arrows and equal sign, plus sign, obvious. What we have left over is an element that has a mass of 14 and a charge of 7. According to our periodic table, the atomic number 7 is nitrogen. And there you go. These are the different types of nuclear equations using 3 examples: alpha, positron, and beta. Again, with alpha and positron, your particle gets smaller. So uranium is bigger than thorium. It weighs more, and it's got a bigger charge. Positron, the mass stays the same, but the charge of the nucleus drops. We went from 20 to 19. Only with beta decay, the mass doesn't change, but the charge increases in the nucleus. So carbon goes up to number 7, nitrogen. In the next video, we will talk about these natural decays, how they occur. Last year you learned about earth science. Uranium turns into lead. Well, it's not direct. Okay? It's either alpha, beta, or positron decay. which means we have what's called a decay series. This means that uranium breaks apart several times before it finally becomes lead. The first step, of course, for uranium is the longest. That's the 4.5 billion years, where it turns into thorium. And then eventually thorium turns into other elements before you finally wind up with a stable lead isotope. So we call that a decay series. We can take a look at that in the next video. We will also take a look at the relationship between these three particles and other radioactive emissions. Thank you.